It's been a little hiatus for us here. You see two of me right now, so I'll get this kind of minimized. I apologize for how this week has went. It wasn't how I had it planned at all. Luckily, I didn't apparently have COVID, but I've got something else that's caused me to have a fever that's knocked me out pretty much every day since Saturday. So I don't really care if it's COVID or it's not. It hasn't been fun. But I started feeling better yesterday. I actually met with a couple people on Zoom yesterday. I had questions on homeworks. And then you're not going to do that while we're that cat, I swear. So if you have any questions, feel free to reach out. I can meet with you on Zoom. I'm feeling better today, so I'm going to try to get through classes today. I've got a couple more this afternoon, but we could find times later in the afternoon today to meet, or early next week. Or even possibly, I usually would meet on the weekends, but I'll probably be doing a little bit of work, just playing catch up. So if you do have a time that works for you, maybe Saturday, honestly, Sunday, I'm probably watching a lot of football. But if you got some time that works for you, let me know. We can maybe try to meet this weekend because of how crazy this week has been. Because we do have homeworks due next week. So we've got the Excel homework, which I believe is due on Monday, right? And missing this kind of week hasn't hurt in the sense that we already worked through all the stuff you needed to get that Excel homework done. The Connect homework is due Wednesday, which we still have a little bit of work that we'll cover today that will help you answer like the very last question on that. So don't think that's a huge deal. It's really just one question, which we hadn't covered information on. So I probably will keep that due date on Wednesday because it really shouldn't have affected your kind of ability to work on the rest of that assignment other than that one question. And having still, 5 days to do one question, I think is okay. But yeah, if you have any questions on either of those assignments, reach out to me. I've had people email me what the work they've had done in the Excel, just to kind of look it over. Like, I'm not sure if I did this part right. Can you check on it? They send me the file, I look at it, and I can give them like help or say, yeah, it looks great, And then any other kind of questions going into things. I know we've been kind of away for a while. Let me make sure there's nobody else waiting here. Just to make sure, right, you guys can't hear me. I had someone earlier said, yeah, you can't hear me. Also, if someone wants to speak up, I think I should be able to hear you too. Not like on the system like in class, but I still should hear you through my computer. Nobody wants to be a brave soul this morning?
I can hear you.
All right, awesome. I can hear you too. So that's perfect. Actually, just in case someone does want to say something, I'm going to turn the volume up a little bit. Apologize for that. So let's go to share screen. Let's go up here. If one of you does talk, I want to be able to hear you, so we'll turn the volume up a little bit. All right, so we're going to start at the beginning. So another thing I'll do tomorrow is, I might even do it this afternoon if I get enough time, is I'm going to tape extra recording that we would have done in class this week and post it either today or tomorrow. You don't have to watch it before class on next Monday. I would advise trying to watch it prior to class on Monday if you can. It'll really kind of get us primed and kind of give us some more background about what we're going to be starting off with on Monday. And then I'm going to try to post an additional lecture next weekend as well that I kind of want you to watch before Monday as well. I know it's not ideal, but that's how we'll kind of catch back up here a little bit, okay? And I'll try to keep it a little bit shorter than like what an actual class would be, because we were actually a little bit ahead of where we should be, so it should be okay. Let me make sure I get everybody in here. All right. So today, where we left off with was talking about percentiles. So let's say you wanted the 75th percentile. So what that would mean is that approximately, if you had looked at every single observation in your data set, right, that means that you're you're greater than 75% of the other observations in that data set. So the way that most people think about this, or have heard this, is usually always like SAT scores or some type of standardized test score. They tell you what percentile you're in. So if I'm in the 90th percentile, that means I'm greater than 90% of the other test scores, right? And that's why I sometimes accidentally say better than. It's really greater than, right? But it also means that I'd be lower than 10%, right? Or 100 minus whatever that percentile I'm choosing P is, right? If I'm the 90th percentile, it means I'm 100 minus 90. I'm lower than 10% of all the test scores, right? So that's kind of what we mean by percentiles, right? It's I am greater than this percent of the data and less than this percent of the data, right? 100 minus whatever that percent is. So you might have also seen something like this, like if you're looking at a pediatric chart, they always have these. This is like the craziest chart because they've got, it's not even 3D, but they've got so much going on, right? They've got age, they've got what your height is, and then what percentile you're in, depending on your age, looking at your height, right? So if I'm 15 and 60 inches, that's 5 foot. I think that's actually close to what I was. I might have been a little bit taller. I was down at the 5 or 10 percentile. That was pretty low, right? But you can kind of find where you would be at, right? So how do they come up with these percentiles, right? Well, for this specific example, they would have a bunch of data on boys' heights at different ages. So how would they choose what numbers were the 5, 10, 15, so on and so forth percentiles? So the first thing you'd want to do is arrange your data from smallest to largest, right? So look at your entire data set, order it from smallest to largest. Give each, so after it's ordered, then the very lowest number would be like position 1, the second lowest number, position 2, so on and so forth, right? And then the very last number would be position n, whatever the size of your sample data was. So to find whatever percentile you're interested in, so like let's say it's the 90th percentile you're interested in, you plug in for P 90, and that's the percentile you're interested in, whatever the size of your data set is, and then this will give you the position, right? And so kind of why this equation is the way it is, I'll give you a little bit of an idea that kind of helps make it make sense. So let's say I was interested in the 50th percentile, right? And let's say I had 100 observations, right? Well, the problem would be is I have 50 observations that are kind of the lowest and 50 that are kind of in the top half. If I was to just choose the 50th position, that would actually only be greater than 49 of the lower ones, and there would still be 50 above it. And so by adding this kind of 1 in here, it kind of puts me in between the 50 and 50 first. So it's going to ensure that whatever value that is, there's 50 below it and 50 above it, because it's the 50th percentile. There should be 50% of the data below it, and then 100 minus 50, or 50% of the data above it. So we kind of have to have that plus 1 in there, because if you just choose the exact position, right, that would be the 50th position, it would kind of put us off by 1. So we have to kind of be in the middle there. So this is the equation we'll use. It doesn't have to be completely clear like that's why we're using it, but that's kind of the intuition behind why. So we plug in the size of our data set and percentile we're interested in. It'll give us a position. So remember I said we arrange the data from lowest to highest. If this position was, say, 3.9, then we know the value that would give us the 50th percentile would be somewhere between whatever values were in the 3rd and 4th position, right? Because 3.9 is between 3 and 4. So it's whatever values are in the 3rd and 4th position. That's what our 50th percentile would be. And I'm just kind of making these numbers up to give you an example right now. We'll look at an actual data set here on the next slide. So if this position is an integer, it actually makes life really easy, right? If I get exactly 3 as my position, I just go to the position 3 and it's whatever number is in position 3, that's the value that gives me whatever percentile I was interested in. If I'm in between two, like the example I gave with 3.9, well, now I'm in between 3 and 4, I have to do this thing called interpolation, right? So I'm a little bit, it's not as easy as just taking the values in the 3rd and 4th position and like finding the average of them. Because if I get 3.9 as the position where that percentile that I'm interested in is, well, 3.9 is a little closer to that, well, I shouldn't say a little, it's quite a bit closer to that 4th position than it is to that 3rd. And so we'll have to start thinking about, similar to what we did last week, one of those values, whichever position I'm closer to, should be weighted a little bit more. So then the question becomes, well, how do I get those weights? All right. So let's go work through an example, and I'll kind of show you kind of what this looks like, what interpolation looks like, where those weights come from. And if I forget to mention something about the median as we're going through this, remind me if I try to continue past this example without mentioning the median. So we've got this metal fund value, right? So we've got, oops, I mean to do that. We've got these 10 funds and they've all kind of returned a certain percent, right? So I don't know, this one lost 56%, this one lost 7, this one gained 8, so on and so forth. Or maybe this was just the actual value of the stock. It doesn't matter which way we think about it. We've got the valuations, we've got them arranged from smallest all the way to largest, okay? So where's the 25th percentile? What value would ensure that 25% of the data is below it and 25% of the data is above it, right? Well, we can use our little formula, right? We've got 10 observations, so we plug 10 in for n. If we're interested in the 25th percentile, p is 25, right? That's just the percentile we're interested in. And we get that the position is 2.75. Well, obviously that's not an exact position. The positions are integers. So we know that the value that gives us that will be the 25th percentile that kind of cuts the data where 25% is below and 25% above, or sorry, 75% would be above, is in this 2.75th position. So that's in between the second and third position, right? 2.75 is in between 2 and 3, but it's a little bit closer to the third position than it is to the second. So I'm going to use the values in the second and third position to then come up with what that 25th percentile value should be. So I'm a little closer to the third position, so I kind of, just a little bit intuitively, I should be weighting that value more, so that 8.09 here should be weighted a little bit more because the position, 2.75, is a little closer to 3 than it is to 2. Okay. So what I do to get my weights is I essentially look at what is my decimal. So 2.75, right? The decimal there is 0.75. So that'll be my first weight. And then my second weight would be whatever would get me up to 1, right? So 0.75, and then my other weight would be 0.25, right? Because that's what would get me up to 1, right? So 0.75 and 0.25. And then I look at, okay, I'm closer to the third position. So I'll take the higher of those two weights, 0.75 is higher than 0.25, and I'll multiply the value in the third position by the higher weight, and then I'll multiply the value in the second position by that lower weight of 0.25. So we kind of think about what that looks like. I would take that -7 and multiply it by that weight of 0.25, and I would take that value of 8 that was in the third position and weight it with the higher weight of 0.75. Now I said this is like the weighted mean, but with the weighted mean we had to divide by the sum of the weights. But given that I told you how to find the weights, what should the sum of the weights always be here? Can we get anyone to guess? So if I'm choosing the decimal and then saying the other weight is whatever gets me up to 1, the sum of my weights should always be, nobody?
Wouldn't it just be the difference to get you to 100?
Yeah, to get me to 100, but right, it's in decimal form, so 100% in decimal form would just be 1. So that's why I don't like divide by anything here, because I'm dividing by 1. It kind of is there, but I don't ever have to really do it. So it's like a weighted mean, but it's nice because our weights always add up to 1. So if our weights always add up to 1, the sum of the weights will always be 1. Dividing by 1 doesn't change anything, right? So once we've chosen our weights, it's just making sure that whatever position, right, you're closer to, 2.75 is a little closer to 3, you make sure that you weight that value with the higher weight. And then the other value, that position that you're a little bit further from, 2, you would weight the value in that position with the lower weight. And I'll show you another couple examples here using these in just a second. So let's see if we can do this. I used to do this a lot last semester. So, oops, except for the screen's going to be a little blurry or clear. So let's say I had 2.5, right? Why would that one actually be pretty easy? Well, if I think about what would my weights be here? If I'm smack dab in the middle of two positions, let me get this person here. If I'm smack dab in the middle, what am I really doing? I'm just finding an average, right? And why? It's because each one, my weights would be 0.5. And what else? Well, it's whatever gets me to 1. So my two weights would be 0.5. So then I would take the values of that -7, what is it, 0.34, multiply that by the weight of 0.5, and then take that 8.09 and multiply it by 0.5 as well. But really all that's doing is adding it up and dividing by 2, right? Because multiplying by 1/2 is the same as dividing by 2. But it would be the same process would get me the answer. Now, what's a little bit trickier is if instead of like 2.5, let's say I had let me write a little bit bigger here so you guys can see something. Let's say I had 2.3, right? So if I have 2.3, what are my weights going to be? Well, I look at this decimal, so that's how I get my weights. So my weights are going to be 0.3, and then what gets me to 1, 0.7. So those are my two weights. But if the position that gives me whatever percentile I'm looking for is the 2.3 position, or 2.3 position, I'm a little closer now to the value in position 2. So the value in position 2 was that -7.34. So now, because I'm closer to the second position, it's going to get weighted by whatever weight's higher. So now it's 0.7 times that value in the second position. And then whatever value was in the third position gets multiplied by that lower weight. So the 8.09 in that third position gets multiplied by that lower weight. Okay. I should have blown this up, or at least just switch the video. I wanted to have the values still up on the screen so you could kind of see the fun values, but there we go. Let me see my work a little bit better there. Okay, all right. So we're using the same values from this metal funds data, but we're just looking at different positions. And the 0.5 when we said was pretty easy because that's really just looking, you're smack dab in the middle. It's really just finding the average of two numbers. Okay. Now these ones are a little trickier when you have like something below 0.5 because 2.3, you don't just use the 0.3 and multiply it by the higher position, right? It's you use the decimal to get your weights, and then you have to think a little bit about, okay, what is this closer to? Oh, it's closer to position 2 than 3. So the number in position 2 gets the higher weight, and the number in position 3 gets the lower weight. Okay. Any questions on that before we keep moving? I did want to say something about the median here. Oh, so if we're talking about percentiles and it's greater than 50 or greater than, or sorry, if the 25th percentile is greater than 25% of the other observations, but it's less than 50% of the other, or less than 75% of the other observations as well, if we think about what that would mean for the median, that would mean the median is greater than, if I think about the 50th percentile, the 50th percentile would be greater than 50% of the data, but less than 50% of the other data, which is really just the definition of the median. So if we find that 50th percentile, we're really just finding the median of our data set. So with that in mind, I'll put myself back up here. If there's any questions, let me know too. I'm going to kind of continue to use this these percentiles to talk about something else. So I'll show you this, and then I'll give you another drawing here real quick. So something you might see in other classes are called, I don't use them a lot. They're called like box and whisker plots. I actually just saw them the other day. We're looking at some grade distribution data for the college. And if you look at quartiles, right? So quartiles would be the 25th and the 50th and the 75th percentile, right? So quartile 1, you're getting the 25th percentile, right? Because it's like if I split all the data into quarters, right? I would have first, 25%, next 25, next and next. So how I get those cutoffs, I need the 25th, 50th, and the 75th percentile. I guess technically I could look at like the 100th percentile of the maximum of the data, but really we only really need those first three to do what we want to do, which is build these box and whisker plots. So once I have these quartiles, right, and we find them the way we just talked about, we find the percentiles the way we just talked about. What I'll do is I'll then come up with this interquartile range, all right? So quartile 3 minus quartile 1 gives me not the range of the data. Remember, the range of the data we said was the maximum minus the minimum. The interquartile range is going to look at those quartile cutoffs, the 25th and the 75th percentile, and look at the difference between those. So what this does, it gives us a little bit better of an idea. So if I thought about income, you know, if I look at just the range, I think we want to mention this when we talked about the range isn't a great measure of dispersion necessarily, because, you know, if I had a data set where everybody made $50,000 and one person made $1 million, the range is going to be the same as if I had a data set where some people made 50, some people made 100, some people made 200, some people made 300, right? It was a lot more varied, but if someone still made $1 million and the lowest person made 50, I would still have the same range. So what this interquartile range does is, because you're looking at the 75th and 25th percentile, it kind of cuts out those extreme values, right? You're kind of getting at more the center of the data. So we're going to use that interquartile range, which is take the third quartile, subtract it from the first. Once I have that, I'm then going to look at that first quartile, and I'm going to subtract 1.5 times whatever that interquartile range was from it. And then I'm going to take the third quartile and add 1.5 times interquartile range to that. I'm going to plot the first, second, and third quartile, and I'm going to plot these lower and upper limits. And then any value that is past these lower and upper limits, we can consider as an outlier, or sorry, an outlier. So if it's an outlier, that means it's such an extreme data point relative to the rest of our data that something weird's going on there. We should look at, like, usually if this happens, like in my brother does some like exercise physiology work, and you know, they use this a lot to identify, like, we had one person who, you know, whose blood pressure or something was way, you know, different than the rest of our subjects. To just put them all in the same pool probably isn't right, because they're probably going to react a lot differently to whatever this, you know, whatever they're trying to implement is than the rest of our kind of subject pool, because they're very unlike the rest of our subjects. So this allows us to identify outliers. I think it's called a Q test. And then so this was always one of my favorite memes. So please don't reject me as an outlier, because you are the Q test, because that's what you use to reject outliers. Yeah, don't try using that one probably when you're out at the bar. So I'll show you what this looks like here. I'm going to stop the screen share. There we go. I'm not sure that's going to be great for the audio, but I'll show you what we're doing here with these box and whisker plots. Because I don't know if any of you have seen the other classes yet, but I'm sure like they'll come up as you. I think they use them a lot in like marketing, maybe. I would say that might be the most common area you'd see. Okay, so so what you would really do is you would take your kind of, let's say my marker works. Let's say you had your first quartile. Let's say that was 50. Let's say your second quartile was 75, and let's say your third quartile was something like, I'll make this easy on myself, 80. Right? So what you would do is you'd first plot these, right? So I go, here's 50, here's 75, and here's 80. Right? So I'd first make a box out of those. Right? So I first make my box of those. Now I need to get the whiskers, or that's what I call them. So how we got those was you took the first quartile and subtracted 1.5 times that inner quartile range. And then to get the upper limit, you took that third quartile and you added 1.5 times that inner quartile range. So all I do now is plug my values in. I know that my first quartile is 50 minus 1.5. Well, I can go back up here, calculate my interquartile range pretty easily. Right? It'll just be 80 minus 50, or 30. So now put 30 in here. 30 times 1.5 is 45. 50 minus 45 would be 5. So my lower limit's 5. My upper limit would take that third quartile, which was 80, add to it 1.5 times that interquartile range of 30. 80 plus 45 is 125. So now I've got this box and whisker plot. Now if I look at my data and I have any observations that are below 5, and I know that my 5 kind of looks like a Z there, but anything below 5 or above 125, I would then plot those points. So let's say I had a data point that was like 140. Well, that's outside of this range. It's not within my whiskers, so to speak. And so I would say I'm justified looking at the data that value of 40 is an outlier. And I can decide how I want to deal with that. It gives me, depending on the situation, I can ignore it. I can kind of use that test as reasoning to drop it from my analysis because look, it's so much different than the rest of my data that it's even past that upper limit that I created. Okay. Let's go back here. Are there any questions on that? Has anybody seen those in any other classes yet? I feel like sometimes people have, sometimes they haven't. Nobody wants to let me know. I wish I could see like virtual head nods. Well, I guess I could if I pulled all your videos up, but that's a little bit hard to keep everyone on the screen. I don't want to have you in kind of the class recording if you don't want to be. So
I saw it in an AP stats class.
AP stats, yeah. So I've seen, I think they use them in like some science classes too, some of the hard sciences, but you might, like I said, you might see them as you kind of continue to progress to higher levels of courses within the business college. All right, where are we at in time? Oh, we're good.
So sorry, I have a question.
Yeah.
So just to clarify, when you're finding the upper limit and upper and lower limit, you don't use the second quartile numbers or number.
No, yeah, you wouldn't use it at all. Really, the second quartile is just there. So if you think about, I'll pull this up just so I don't have to keep switching back. Make this a little bit bigger for everybody here. So if you think about like that drawing, see the second quartile is plotted there, and it's really just giving you an idea of where the middle of that data is. You kind of notice, so on this drawing, you kind of notice that second and third quartile are really close to each other, right? And so that tells me something about the skew of the data, right? Because it's telling me that there's kind of a longer, what would be left tail there, because the first quartile and the median are further apart than that second and third quartile. So that's generally why people like to use that. I'm not going to go, I'm not going to test you guys on using that to determine the skew, but that really is a byproduct of it. So once you see where that median is at, if it's closer to the third quartile, the values at the higher end are closer together. So your tail there on the right-hand side, the higher end is smaller. So you have a short right tail. And if it's further from that first quartile, the data on the lower end is further spread out. So you have a longer left tail. So you actually can look at that, just the box part of it, and get an idea about what the skew of the data is. Right? That's really why the median's there. Yeah, that's a good question, though. Any other questions before we kind of keep moving? That was a really good question, actually. Okay. So the next thing I want to kind of talk about is, up to this point, we've really only looked at one variable. So we found the mean of a variable, we found the variance of a variable. We might also want to look at what's the relationship between two different variables, right? So maybe we've got, two variables, and we want to know if one goes up, what happens to the other? I think I mentioned this when we were talking about scatter plots. If I see the healthcare expenditures of a country go up, does that increase life expectancy, decrease life expectancy, do nothing to life expectancy? Well, we might be interested in these things, right? If I spend more of taxpayers' dollars on this one thing, what happens, right? If I spend more money on policing, does crime go up? Does it go down? Does it not change at all? It's a valid question, right? And I don't want to be spending the money if it doesn't have any impact. Right? So we have two measures we'll talk about now. At the very end of the course, we'll actually get to an even better measurement of kind of the relationship between two variables, but it still has to start out, the discussion has to start out thinking about covariances and correlations. Right? Now, correlations, we can also call them, actual statistic we'll have is a correlation coefficient, right? But usually we shorthand just call it what the correlation between two variables are. Right? So we've got two different, just like everything else, samples and populations, just like for means and variances, we've got population covariance, sample covariance. So we've got two variables. Here's our equation, right? And I'll kind of walk you through this a little bit more with a data set here in a second. But we try to read this formula based off what we've already done with the variance. We see that we're going to write the covariance using still that sigma. So it's a little confusing because when we had sigma, right, that was the standard deviation of whatever variable we're looking at. But we're only looking at one variable. Here, we've got, this is the standard deviation. No, it's not standard deviation because we've subscripted it with two variables, right? So once you have this subscript with two different variables, you're indicating that I'm not looking just at one variable, I'm looking at what the relationship is between two. And so now this sigma of whatever x, y variables you're looking at are, now it's kind of representing, this is a covariance. Okay? I know it's a little confusing. I mean, I didn't choose the notation. If it was up to me, I probably would have chosen some different Greek letter. But this does represent our covariance sigma, and then you subscript it with whatever two variables you're interested in. So if it's education and income, you would write, subscript E and I, or however you wanted to abbreviate education and income there. Okay. So what we would do in an example like that, let's say I had education and income were the variables I'm interested in. Right? What's the relationship between them? If education goes up, does income go up or down? So I would find the average of both, right? I'd find the mean, my x variable is education, I'd find the mean education level, or number of years of education. I'd find the mean income, so if my y variable is income, I'd find the mean income. Then for every single observation, I'd go to the first person, I would take their education in number of years, subtract the mean, and then multiply that by whatever their income was minus the average income of everybody in the data set. I then go to the second person. I do the same thing. I go to the third person, do the same thing. I go all the way from the first to the very last person, and then I add them all up, right? So we're not squaring anything here, but we are kind of multiplying two differences, right? And then when I'm all done, just like with a variance, or we divide by the total number of observations in the data set. If it's population data, it's capital N. If it's sampled data, then the covariance is going to be lowercase s, and then whatever the two variables are as your subscripts. It's the exact same process, but once again, just like with the variance, we divide by n minus 1 because there's some bias we need to correct for, as opposed to just dividing by n. Okay? Like I said, I'll walk through this with an actual data set, and I think it'll make it a little bit more clear, but that's kind of the process that we're doing, right? And I'll explain when we have some actual numbers, what's kind of going on here in the numerator to give us either a covariance that's in one of three ranges. It could either be positive, negative, or pretty much zero. So what that would tell us is a covariance that's positive says these two variables, like as one goes up, the other one tends to be higher as well. If it's negative, it says, well, as one of these variables goes up, the other one tends to be lower. And then if it's about zero, it says as one of these variables goes up, the other one doesn't really change much, right? And so kind of the positive is evidence that there's a positive relationship between the two things. Less than zero, evidence there's a negative relationship, and about zero, there just really isn't a relationship. Okay? So let's look at this actual kind of data here. So I had I grabbed some CDC data on height and weight, and you can kind of see, this had a bunch of different people in it. I was kind of surprised the average is a little bit high, but it might have been, this might have accidentally ended up with a few more, a higher percent of females, and I think there was also some younger individuals in here. It says adults, but I think I accidentally might have grabbed some people that were still like 16, 17, 18. So maybe the height's average height's a little bit lower than you would expect. But what I did was I went through, if I had these two columns originally, height and weight, in Excel, hopefully we can imagine by now, very easy to find the mean, right? Very easy to find the mean height. I would just equals average, select the whole column of data. If I've got weight, equals average, select the column that has weight. And now I've got my two means, right? So the average person in this data set, a little bit older data, was what, about 5'4" and about 188 pounds, okay? So the first thing we could do, if we want to break this down into steps, we don't have to break it down as much as I did, but just to kind of show you something, I broke it down really kind of minutely. So the first person, I need to look at what's the difference between their height and the average height. My bars got kind of messed up here, but hopefully you can kind of see there's bars over here to represent the averages. This is sample data. So I'll take this person's height, 70.4, and I'll subtract the average height. I put that number down. And the next thing I needed, this is kind of the final thing I need. The next thing I need is the difference between their weight and the average weight. So I look at their weight, it's a little bit below the average, right? So this one observation, notice this person was above average height, right? 70 inches is greater than that, about 64, but they were below the average weight. So this one observation was evidence that, well, this person was above average height, but they were below average weight. So they're evidence that height and weight actually are kind of working in opposite directions. They had an above average height, but they had a below average weight, right? So that one observation is evidence that height and weight have a negative relationship. Now, obviously, intuitively, we know that that's not true, but this one observation, it looks like that, right? So we go to the next one, right? Now we've got someone who is, actually, I'm gonna skip them because it's very close to the actual mean. Look at this person, right? They're evidence that, well, they have below average height and they also have below average weight. So notice below average height and below average weight, that's evidence. That one observation is evidence that, yeah, when you're, when you have a lower height, you would also tend to have a lower weight. But we have to go through every observation, right? So there could be observations that are evidence that there's a positive relationship. Some could show you evidence of a negative. But at the very end, what do you do? Well, when you multiply these two things together, you add all those up. So every time there's evidence of a negative relationship, right? Notice like on this one, when I multiply the differences, if one is above the average height and the other is below the average weight, I'll get a negative value because a positive times a negative is a negative. So that would be evidence of a negative relationship. So it adds a negative value to the numerator. This one where I had pretty strong evidence that if I was pretty far below the average weight, far below the average height, I'd also be very far below the average weight. Well, a negative times a negative, right? Because they're both below the average, gives me a positive. It's evidence that these two things tend to be on the same side of the averages. If I'm shorter than the average person, I tend to have a lower weight than the average person, and vice versa. And notice when I had, this was a pretty strong evidence one. I mean, this person, my God, they didn't weigh 100 pounds. So this was very strong evidence. So notice it adds a very large value to that numerator. This one, it was evidence that maybe they are on opposite sides of the averages, but not strong evidence, right? This was like not, it wasn't that much above the average height and their weight wasn't like very much below. So it adds a much lower value to that numerator. You could go through every single kind of observation and use this logic, but really every observation will be influencing that covariance a little bit. So really what the covariance is telling you is not that for any one person, their height and weight will be on the same side of the average, but that overall, when we add up all these values here in this last column, that if we get a positive or negative value, we're saying that over the entire data or over every single observation we have, it looks like on average, there's a positive or a negative relationship between these two variables, okay? Any questions on that before I continue to keep moving here? Hopefully it makes a little bit more sense, like seeing the actual numbers there. So I actually went through and did this with the data, and you get about 76. I mean, that's what I would think we would expect that, right? I mean, you'd expect height and weight to have a positive relationship. If we controlled for other factors, they for sure would, but without even controlling for anything else, if I'm 7 foot tall, I can't weigh 100 pounds. I don't think I'd be living if I weighed 100 pounds, right? So it's great. We now know there's a positive relationship between height and weight, but how strong is that? Can I compare that to the relationship between education and income, which, spoiler alert, that tends to be positive as well? Well, when I think about the covariance, we have a little bit of an issue about comparing to other relationships. So, well, I guess I'll point it out before I praise the correlation coefficient. But if I think about my height weight example, when I'm building this covariance and I'm multiplying the x variable by the y variable, what I'm really getting is what? Inches times pounds. So my units is like inch pounds, which I don't really know what that means. If I think about education and income, I'd be multiplying the units of years times dollars. So I have year dollars. You know, like I don't really know how to think about the units there, and I definitely can't compare year dollars to inch pounds. I don't even know that. First of all, we're comparing two things that don't even exist. So what do we do, right? How can I deal with this? And also, the covariance is going to be greatly influenced by just the overall size, right? If I look at covariances for income, I mean, I've got incomes like up $50,000. I'm just going to end up with much larger covariances than when I'm looking at averages of like 60 and 190, right? So how can we solve this problem? Correlation coefficient, right? So what the correlation coefficient will do, and you could go through a mathematical proof to show why. If I have time here, I might just give you a rough idea, but it's not, you don't have to know it. You just have to know the end result of why, or you need to know the rules of the correlation coefficient, not necessarily know exactly why they exist. I'll kind of show you a little bit. So here's our correlation coefficient. The equation is just going to be take your covariance between these two variables and divide it by the standard deviation of each variable. Okay? So you can write it as a population. We'll use this Greek letter rho to signify that. And for the sample correlation coefficient, we'll use lowercase r. Okay? So all you do in each case is take the covariance between those two variables, and then if it's a sample correlation coefficient divided by the two sample standard deviations of each variable, it's population divided by the standard deviation of each variable. Right? It's as easy as that. Right? So, okay, so the properties that results in, and I guess I'll try to give you an idea about why in just a second, is it makes sure that when I divide by the standard deviation of each one of these variables, it makes sure that my correlation coefficient at the highest it could be is 1, and at the lowest it could be is -1. Okay? And you can, like I said, you could Google search correlation coefficient bounds proof probably, and you probably could find it. But it has to be, once you divide that covariance by the two standard deviations, they'll have to be between 1 and -1. Okay? 1 would signify the strongest positive relationship possible. -1 represents the, not the weakest, but the strongest like negative relationship possible. Okay. Now, yeah, the weakest relationship would be if I find a correlation coefficient that is about 0, right? That's evidence that there's no relationship between these two variables. But -1 is the strongest evidence of a negative relationship. Excuse me, +1 is the strongest evidence of a positive relationship. And then you've got your anything between -1 and 0, just as it gets closer to 0, the weaker the negative relationship is. As it gets closer to 0 from the positive direction, the weaker the positive relationship you have. Okay? So why is it always going to be, and also kind of the nice thing you can imagine. So if I have like inch pounds here in the numerator, when I divide by the standard deviation of x, well, my x variable is height. So when I divide by height, the heights kind of cancel. And when I divide by the y variable standard deviation, that was inches, now the inches kind of cancel out. So you can kind of see my units will cancel. And so the correlation coefficient is this nice, just non-unit measure, right? There's no units to it in the sense that it's not dollars or inches, anything like that. By dividing by the standard deviation of each one of these variables, it can cancel out whatever those units are, okay? So why does it have to be bounded between 1 and -1? We can kind of think about, we look at this equation here. With a variance equation for just one variable was the sum of xi minus x bar squared. But then to get the standard deviation, we had to take the square root of it. So you can kind of imagine like I'm taking the square root of the sum of the x's minus x bar squared. Square root of the squared would cancel. Now that I'm dividing this by just xi minus x bar, those would cancel. You know, that's not the real mathematical proof, but that's kind of where it comes out to why it's always going to be somewhere between 1 and -1. Like I said, I'm not going to like make sure we understand exactly why, you know, every line of the mathematical proof as to why it's bounded between 1 and -1. We just need to know that it is. Okay, and the closer to 1 it is, the stronger, you know, positive relationship it is. The closer to -1, the stronger the negative relationship is. Okay. Let's see if there's any questions. Any questions here? I'm going to go through a little bit more before we kind of end today. Okay. So it's really as simple as once you have the covariance, once you have the standard deviations, you're just plugging those values in, right? So if I have a covariance of 76 from that CDC data, it's pretty easy in Excel to find the standard deviation, right? stdev.s, select the variables, or the variable that I'm interested in. So I did that, found the standard deviations. Now it's just a matter of plugging them in. I get about 0.45. So, you know, the relationship between height and weight, although it's positive, it's not like the strongest, right? It's kind of like in the middle of the road, right? It's between, almost exactly in between 0 and 1, right? And so it's a, you know, it's not the weakest relationship, but it's not the strongest one either, right? And we could go through other variables and look at what their correlation coefficient is. And if it was greater than 0.45, we would say, well, that's a stronger positive relationship than the relationship between height and weight, right? And yeah, that's the, you know, now with this correlation coefficient, we can compare across different variables, right? So if I said the, you know, correlation coefficient between education and income is 0.8, well, that's a much stronger positive relationship than that exists between height and height and weight. Yeah. You know, and really what we're doing, you can kind of imagine this from a scatter plot as well. It's really just, you know, taking that visual scatter plot and putting it down into one statistic, right? If I had that line of best fit, and I'm kind of trying to get like one statistic that represents what that line of best fit would be, okay? Or what that slope of that line would be. So I got a sample question in here. I'm not going to spend a lot of time on this because I think it's pretty easy. I think this is pretty easy. If I tell you the covariance, so I will give you an online quiz today. Haven't had one of those in a while. But if I give you the covariance and I give you the two standard deviations, it should be pretty easy to just take that covariance and divide it by 8.13 and also divide it by 48.51, right? Now, if I just think about the range here, what do I know this correlation coefficient has to be between? 1 and -1. So automatically I can rule out an answer like this. Oh, not like this. An answer like this, 1,969. What I also know is, well, look, if I find that the covariance is positive, my standard deviations are always going to be positive. So really the sign of the covariance tells me the sign of the correlation coefficient. Remember, they're both getting at the relationship between the two variables. The correlation coefficient has just been scaled. So the sign of the covariance shouldn't change once you calculate the correlation coefficient. So if I look at the sign here, I know it should be positive. So I can rule out D as well. And then from there, it's just a matter of plugging the numbers in. So you take 330 divided by 8.13 times 48.51, you should get about 0.84. I got another question there. You could like play around with this one. You could try to recreate this, make sure you can get, it's really the same as the previous one, just another example. So if you're kind of wanting to do some more work, wanting some more practice before we take the online quiz, you could try to work through this one, make sure you can reproduce the answer of 0.06 as well. I left this, I'll leave this in here. We'll kind of end class here pretty shortly. We won't watch this together, obviously, because we can't all be in class at the same time. But I highly suggest watching this clip from The Daily Show. You just copy and paste this URL, and I'll start playing. It's pretty funny. Maybe I'll even like put a link somehow into our class's YouTube page so that the video will like pop up there. But it's some economist talking about the relationship, right? Correlation coefficients between looks and income. And it's kind of interesting. His actual this was actual research that he did and got published. It's very interesting, but it's very funny. Jon Stewart puts a pretty funny light on it. So I'd highly suggest watching it if you've got some time and you want to laugh for a little bit. But he does find that there's a pretty strong relationship, specifically for women. So they like sent out like identical resumes or something, but then had different pictures attached. And so when they ranked these people in percentiles of attractiveness, if you were in a higher percentile, you get a higher number of interview requests, even though your resumes were literally identical that were sent to the companies, which is sad, but that's what the data showed. So they show there is kind of this, I'm going to say discrimination, but kind of this bias that exists. Right? So we will start. I'll start that first. So the additional video I'll be recording, I'll start here and I'll kind of introduce the idea of probability and probably get up to the point where I'm talking about contingency tables. And then on Monday, I'll kind of expected that you at some point this weekend or at some point prior to class Monday, you got on and watched that additional video. And we'll dive a little bit deeper into probability and kind of start the next chapter. Okay. So what I'm also going to do is get that the next Learn Smart up. So watch the video, do the 10 minutes or whatever it is to get through that Learn Smart before class on Monday. So that we'll kind of be prepared to kind of jump into this probability. It starts to get a little bit tougher from here. So I'm going to end class there. If you guys have any questions, I'll kind of leave this up for a hot second. But thanks for getting on me. I'm sorry this has been a crazy week. If you have any questions on the homeworks or anything moving forward, please let me know. I'll get an announcement up about kind of the Learn Smart and then the additional recording on Canvas later today as well. Okay. All right. You guys have a good day.